will induce, it will have equilibrium, right? Let me use a different color for this. I do apologize. So not everything look the same. It can be very confusing. So this is our shear X, Y. And based on the equivalent condition, this will be our shear Y, X. Okay. Now, the interesting thing is this. Okay. When we calculate shear or the shear stress, the area of interest is in this direction. Okay, the vertical plane. Okay. Now, if you look at the diagram on the right-hand side, right, where failure occur is not on the, now I'm going to highlight the yellow surface, okay? It's not on this surface that is the surface. The yellow surface that I've drawn, pardon me, this diagram is not superb. I have to modify a bit. I do apologize, okay? I think I missed out on something down here. Yeah, I missed out down here. I should have drawn this. Diagrams are important. You get it wrong, it can be very confusing. Okay. So I'm going to highlight the yellow region. These are the same surface. The yellow region are the same surface as the one on the left-hand side. Okay. Now, the direction of failure is not on the yellow highlighted surfaces. You can see whether, however, the direction of failure is in this direction. So I'm going to call this our delta. Can you see that? When the delta increases, okay, so this is what we call the slip. Okay, so delta is the slip, okay, parallel parallel to the schematic layer. Okay. Now this yellow highlighted point, okay, in this direction, the geometry did not change. Right? The geometry, you can see down here, the geometry did not change. Right? So if I draw an exploded view, okay, if I were to sketch an exploded view of this section over here, okay, I draw a exploded view. So I'm going to draw a bigger view for you, right? An exploded view, right? So this is okay. The area that we are calculating is this area, right? Stress is going to force divided by area, everyone, or the surface of interest. So this layer, as I mentioned before, this height or this thickness over here in this direction, the geometry did not change. Okay, so both of this geometry did not change. However, what you see is you are having slip, right? So this is our slip direction. Okay. So what is the confusing bit? Okay. The area of failure or the surface of failure or the shear stress is acting on the yellow highlighted surfaces. But the failure is acting on the blue direction. Okay. So the only way that this is logical is where we have our equilibrium condition, where shear xy is equal to shear yx. So what we are calculating, okay, if you look at the shear force direction, is a surface that is perpendicular to the shear force, right? However, the failure on the blue surfaces and the yellow or the shear stress on the blue surface, which is also equal to our shear yx, is equal to our shear what? Xy. Okay. So what I'm trying to say is this. No doubt the surface is what? Right? The blue highlighted surface is where failure will occur. Relative to the shear force is perpendicular. True. But the slip will also occur on the what? Blue line or the blue heighted line. Okay. So you have to get this concept straight first. Okay. That is because later on you'll be confused. Okay. Shear force is here, but why? Like why failure will also occur on the blue line or the blue heighted surface? Because the blue highlighted surface relative to the shear force, it seems to be what? Perpendicular. It should be normal stress, but no. This is still failure induced by shear. And that's where a lot of times students are confused. Okay. Why are we calculating? Okay. Why are we calculating the yellow surface where the failure, excuse me, occur on the horizontal surface? Okay. So we have to have this definition clear first. Understand? I know it's very abstract for now, but if you have question on this, okay, I will spend time to explain to you. You're okay with it, or you all want me to repeat? I don't hear anything. Okay, so it's very abstract. Okay, I want you all to like it's okay. Okay, I want you all to like it's, as I said, it's not difficult. It's just abstract. You have to know why the failure is occurring on the horizontal plane. No doubt we are considering the area on the vertical. Okay, so this topic only has two major formula, and I will introduce you to the two major formula. Okay, so the first one is known as the horizontal shear per unit length. Okay, and is also AKA, also known as shear flow. Okay, also known as a shear flow. So the formula is Q is equal to VQ over I. Okay, so this is one formula where Q is the shear flow, V is the shear force, Q is the first, okay, all of a sudden I can't spell, first moment of area, and I is the second moment of area. Okay. So when we look at units, this is in meters to power 4. This is in meters to power 3. This is in Newton. Okay. So if we do unit balance, or we look at the units, the shear flow, so you have Newton meter cube over meter 4. You get rid of this, you get rid, so this will be equal to Newton per meter. Okay. So that is our, now, what do we mean by shear flow? Physically what it is. So if we were to look at the cross-sectional view, okay. So now I change my transformation direction now. This is our Y. This is our Z. This is rotation about X. Okay. And this is our cross-sectional view of our structure. Right. And if this over here is your Vy, so the shear force in the Y direction, Q will be in this. This is our Q. And you will see that I draw them in different length. Okay, so the longer arrow, okay, the longer arrow indicates higher Q value. Okay, so that is what we mean by, so this is a cross-sectional view. Okay, and then I will tell you what is the first moment of area. What do we mean by first moment of area? Okay, so let me go to the, you have all this already. So Q is equal to A Y bar. Okay. So A is defined as the defined area, which is in meter squared, and Y bar is known as the distance between the centroid, or the global centroid, and the defined area centroid. Okay, and this over here is in meters. That's why the units is in what? Meter cube. Okay, so that's one formula. The next formula, now I want you all to take note. This is confusing to find. Okay, a lot of times students have problem. It's always the first moment of area. Okay, so that's one formula, or one major formula, which is Q is equal to VQ over I, and this is the formula for the first moment of area. Now, more importantly, is the shear stress. Okay, so the shear stress, okay, the shear stress is equal to tau is equal to V. I will write both components. Okay, so you can have y or z. Okay, so Vy, and I want you to look at the formula. So Vy over Iz